Ranak everybody, you're on the channel FEArytales, and I have some video about how the different statements influence to the result. But I have a complaint from the viewers that I didn't talk about one very important things. That not only difference in statement produce a different result. Sometimes when we're using the numerical software, finite element analysis and so on, like Ansys software, Siemens FEMAP, Altair, Hypermesh, and many others, especially any type of software, we can sometimes, very often, if we talk in all cases, we also can say we obtain the different result not for only the different statements, but for the one result. So we have the one result file, but using the different option of visualization, we can obtain the different numbers and different pictures. That sometimes is very important. So let's today talk about this. We have a nonlinear solution here for the task which already presented in at this channel, and you can download the model to repeat it by yourself. This is equivalent stress, and this is now a nonlinear behavior with plastic materials and with different materials in different objects. So we have nonlinear steel, we have nonlinear aluminum, and we have the linear steel here. But it's not very important, it's for complexity and for results which can be different. So we have the results here. We have the total deformation, we have equivalent elastic strain, equivalent plastic strain, which present only for materials which work non-linearly. We have equivalent stress and some other type of the stresses. And it's very important that almost all results have some additional options. If we take a look here, we will see the display options which shows. And this option can be changed by viewer, and they affect the picture which we see and the numbers which we get. So let's try it. This is a copy of equivalent stress, and we have the same options. So those two pictures are the same for this moment. So let's change this averaged result to unaveraged, and let's recalculate this result. And you'll see that this number change, this picture also have some small changes, but in general the qualitative picture are the same for this changed unaveraged result and for averaged. Yep, we have some small places when it change, some migration of maximum, result of concentrator, but in general the picture are the same. But if we take a look here, we have almost 900 megapascals here, and for unaveraged we have almost 1300. So it's almost half additionally to this one. Okay, 30%, but 30% higher. And if we change this result for something another, for example, nodal difference, the picture will be very different. the picture are not the same. It's very different. Different digits, numbers, different pictures, and we can see that we here will not obtain in any sort of the scale the same type of result as we can see on a previous picture. Also, we have the nodal fraction, and it's also not the same, and we obtain the very small result here. Just a moment, we will raise that picture, and we see almost 16, not 900, not 1300, but simply 16, not 100, 16. So some users can change these parameters, can make a screenshot and use it as a result sometimes, and say, you see, we have a good result. It's a better result than someone ever can obtain, and so on. Sometimes people, depending on their aim and their target, can change those type of result. For example, if they want to obtain more money, they change result on average, show to the customer, say, you see, you have some problem, the result are very high, we need to do some changes. People give the money, then user simply switch the type of result to average and see, you see, we do a lot of work and now construction work well, so this is it. No, it's not. But some people do this, some with understanding what they're doing, and some even without understanding. Simply they try to find those digits which they like more. So it's very hard to explain everything here on this model, because we have linear and non-linear behavior, because we have contacts, because we have a lot of different things. So let's switch to more simple tasks. So we have a simplified model. It's only this crank, and also it presents Excel to receive the force for simplified loading process, and all this object was made with different type of mesh. We already have a video about how to do the different type of mesh in one task. The link will be here, so you can use it. And now let's talk about the result. So, what type of mesh we have here? First of all, we have very simple difference. Those both was meshed with tetrahedral mesh, with tetras, and those meshed with hexahedral mesh, so it's hexa. But it's not explained why we have 2 tetra and 2 hexa. And if we select the nodes, we can see that one of this model from both tetra and hexa have a lot of nodes, and especially they have mid-side node. So it's second order element with quadratic function and so on. And this hexa and this tetra is nonlinear in sense of using parabolic equation inside of element. And those 2 objects, this tetra and this hexa, has only nodes at corner, so it's linear first order tetra. and first order hexa. So that's the difference. We created with those additional properties, with those additional options. All objects have the same material. All 8 objects have the same material. For this moment, it's a steel. It's very important because for this moment we will return later. So it's almost maximal simplification of these tasks. And we have a lot of results. We have all type of official results that are present here in the solution. We have a deformation, we have strain, stress, energy, and structural error. And some of these results doesn't have option which can be changed. They doesn't have display options. For example, structural error and strain energy. Why so? We can explain in a different, in other video if you want. For today, we will not explain because it's too many time need. When we talk about total deformation, we have the one option which are not affected result here, but affected result here in our graph. But unfortunately, I have some visualization error, so the graph are not present here. We can see the number of dots here, but we can't see those graphs. So let's explain the difference and the options. The options is here, separate data by entity, and for the first one we have no, and we have only 2 dots here on the 0 and here, and also the third here. So it's minimum, it's maximum, and it's average. 3 dot, not 2, 3. And for those option, we have the separate data by entity, and we have a lot of dots. And the number of dots corresponding to number of this object and to the result. Minimum, average, and the maximum. And we can see here a lot of these result. For every object we have 3 points. So this is the option. This is option which is very important because we can see the graph for every part separately, not for the whole model. It can be useful for the real object, for real construction, when everything is different, and for the scientific project when we try to do estimation and compare the result for some objects. So for all other results, for the result of the strain and stress, we have couple options. So if we open all these folders, we can see that all these results have the same number of options. The only folder plastic now is suppressed because we have the linear material and we doesn't have the plastic strain here. So what is the difference? Let's talk firstly about the equivalent stress because it's more simple to view and more simple to understand, because if we select, for example, equivalent strain elastic, we can see that the numbers is very low, and it will be very hard to sometimes understand the difference and so on. Here we have very simplified result, and we have 100 and 1483, so we have almost 1500 of megapascals. We can see that all tasks have almost the same result for their deformation, for the strain, for the stresses, almost the same between all these tasks. It means that we have mesh not very bad. It's not good, but it's not very coarse. And this size, which is very important, produce the mesh which can be analyzed with the student version of Ansys, because the student version has a limitation about 125,000 of nodes and elements. We have about 40,000 here, so we can you can repeat it without any problem if you want. So let's return here. We have not ideal, and this result is worse. This result and this result not very good. This result much better, and we will see it later. But almost the same, almost. So we have, I don't want to say good enough mesh, but let's say good enough. And the result we can see here almost 1500s, 1483. So let's talk about unaveraged. And result with unaveraged is very different. It's have 1896, so it's about 20% higher for now. We have almost the same picture. We can switch, and we can we can see that the distribution of stress have some changes with the option averaged and unaveraged, but in general it look almost the same. But those digits are very different. Additionally, if we take a look more detailed and more close to those mesh and to those results, we will see the difference. So when we take a look to the averaged result, we can see that we have very smooth picture here. Yep, we have the gradient between those two regions, between those color and those color, but it's the option about smooth contour and not smooth. We use not smooth contour bands to better understanding of the difference. And yep, sometimes it have some peaks, like here, some waves, but in general it's continuous. We have the one line which have some waves, some peaks, but it's the one line. We have this line here on the best meshes, so in hex mesh with the second order element, and we have the same picture, the same behavior on the worser, on the coarser mesh with the linear tetra element. We have already video about comparison of different type of meshes. You can find it here with the link, which will I add. And in general, we can see that it's one line, the same as the first. But when we switch from average to unaverage, the picture is very different. We can see here any smooth line, even with peak, because every element colored with their own color. And if we take a probe, we can see that no matter when we try to obtain the probe, we have the one result. If we switch to another element, the results are changed. But inside of element, we have the same result, because linear tetra have the one stress and strain value through the element. If we came here and scale, we can see that we doesn't have the one line. We have a lot of blocks. Even if the line look like the one, we have steps, we have peaks, we have bricks. And we can see that our result through our elements has changed from the one point to another point, from the one point to another. The same situation we can achieve, and we can explore here on the hex linear mesh. The type of stripes, the type of graphs look different, but behavior, as you can see, the same. On a different corner, we have different type of result, and in another elements we also have the different result. And for non-linear tetra, for quadratic tetra, for second order, we can see the same situation, that during our element the stress has changes. So unaveraged result show the whole picture of stress distribution, not averaged by the model, by the nodes, but unaveraged in any element. When we talk about averaged result, for every node, we obtain a result from every element which have this node, make average of this result, and then create a linearized stress distribution between the nodes. That's why we have so smooth line without any bricks, with some waves, with some peaks, but without any bricks. So the nodal difference, it's very important result which show the difference between the elements which attach it to one node. So we have, for every node, we have the stress value in this node in all elements which connected to this node. And in result, we have the minimum stress in this node, in some element, and the maximum stress for this node from all this list for one node. And the stress difference is maximum minus minimum for this node. This why this difference can be very big, and especially it big for the coarse mesh, for the linear tetra. And especially in the place near the hotspot, near the concentrators. So, nodal fraction, it's an interesting result where we have the nodal difference, which divided by average stress in those result. So it's not in megapascal like the nodal difference, unit megapascal, like unaveraged or averaged. All these variants are in megapascal. But nodal fraction, it's a ratio between the nodal difference and averaged value. So the element difference are almost the same, but from the point of view of the element. So we have one element, and this element have several nodes. Each nodes have their own stress for this element. And we have the minimum stress, node stress for this element, and the maximum stress, node stress for this element. And the element difference is the difference from maximum to minimum inside of one element. In reason that linear tetra have the constant value, and in all nodes we have the same values, the nodal difference are present, but the element difference are not. In all other variants where we have different variants of node stress inside of one element, we have for every element the element difference. And the same element fraction, it's a ratio between element difference and averaged value of element stress. So it's very important that nodal difference, nodal fraction, element difference, and element fraction is very important values which can help in understanding of how coarse mesh is. Do we need to improve mesh in the place when we need important information, and so on. And the element mean, it's simply general 1.1 value for one element, so it's the thing by which dilated element difference in element fraction. So for nodal fraction we use the nodal difference which divided by average stress. For element fraction we have element difference which divided by element mean in general. So that's the physical and mathematical sense of those type of result, no matter what they are presenting here. Those type of result doesn't present for their total deformation because we have only one value of deformation in any node. We have three different values for x, y, and z direction, and sometimes for rotation, but it's constant value, it's constant vector. So they change from point to point, from node to node, and they doesn't have difference. But then all this value taken for every element, and for every element we obtain strain and stresses. That's why in deformation we doesn't have those type of difference, because it's for wall model, and for the strain and the stress we have. In reason that the error and the energy based on deformation and based on integrational characteristic, they also doesn't have those type of difference. They are the same for the node and for the element. One value for node, one value for element. So that's why we can only see those type of result and understand how it look, how it work. Okay, so what is very important? That's the reason why when you create a report for the finite element analysis, you not only describe the number of nodes and elements, you not only show the mesh for the wall geometry and for some parts of the geometry, which is important, you not only say what software you use, but you also must write an option which you use when you visualize the result of your calculation. Because depending on software, depending on options, you can have the very different type of result. Later will be a couple additional videos, one with the Siemens FEAMAP and one with the Ansys APDL mechanical or classic Ansys, when we show that different software can also open the same result and visualize it different, even with averaging, depending on type of averaging and depending on other algorithms which is implanted into your software. So that's why you need to write the type of software, the version, the type of option which you use. And in most cases, methodology which use it, for some cases, sometimes have a list of software and options which you must use for visualizing result and for analyzing the result and the result quality, the mesh quality, because it's very important. So this the main explanation, but also we have some additional calculation, and we will talk about them later. Thank you and goodbye, and if you want to support this channel, you can use this link. Bye.